All right. My name is John Ashley. I'm the Chief AI Architect for the global public sector at NVIDIA. I also, in a uh, more than a few years back now, in my 16 years at NVIDIA, I supported our early efforts in the radio astronomy space, along with a number of my colleagues. So it's a pleasure to be uh, speaking here at the FTSky program, thanks to our hosts, ICTS. And maybe roadmaps sold the talk a little hard. Let's talk about trends in AI advances for discovery. Um, and let's see if this will actually advance at this point. Fighting back. So I want to talk about three things. I want to talk about the data deluge, and that'll be quick because we all know what's going on there. But then I want to talk about how that's driving the evolution of hardware for AI and therefore for other things, right? One of the big things that I think back when I was supporting radio astronomy, back in the earliest days of radio astronomy until now, um, radio astronomers are not a market that computer vendors are chasing uh, to make their next $1 billion, right? It's a vibrant market. It pushes the envelope. It stretches our capability and our imagination, but it is not the favorite of Wall Street. And so understanding, where the wave is going in terms of technology so that we can harness it, so we can apply creativity and look at the bottlenecks in our systems and the things we want to do is going to be key. And that's going to sort of bring us to the last part of the talk as we sort of think about how AI is going to drive capability and what things are coming and what trends are coming that are going to be useful to us for science. Um, so that's kind of the plan. Um, and I'm happy. Uh, I can't really see the room very well. I'm happy to take questions as I go or just leave them at the end. Whatever from an organizational perspective, whatever works best for you. So just let me know. Um, don't probably have to tell you a lot about the data deluge, right? And I apologize. I'm supposed to use standard slides, so I'm going to talk to some things that aren't on the slides. Um, really, though, the biggest challenge that we have is that the universe is incredibly parallel, and our ability to gather signal from instruments, whether that be a radio antenna, a camera, uh, a electrosound or an ultrasound probe, whatever it might be, we can generally acquire that data far faster than we can then move and process that data, right? Speed of light is an issue, bandwidth's an issue, moving data is the most expensive thing from an energy perspective. Um, but all these streams of sensor data, uh, there's really important information in that. And the more of it we can take and the faster, the better. And so you'll hear a lot this morning about a product called NVIDIA Holoscan. It's software and it's designed to help us um, get data off a sensor over a wire, in this case, right, Ethernet, UDP, some protocol over a wire or fiber, um, and get that into the compute engine as quickly, simply, with as little latency and as little loss of bandwidth along the way as possible. And I'm not going to try and do I'm not going to give you a lot of speeds and feeds or anything, but I do want to talk about trends. And so certainly one of the things that we always have faced in the data acquisition space is sensors are frequently analog and there's all sorts of messy noise, there's all sorts of tuning, there's all sorts of messy issues with sensors. And so we're frequently putting some kind of an ASIC, some kind of an FPGA, something in between that sensor to get it onto a digital signal and moving over something that's commercially viable. Obviously, back in the early days, everybody wanted to build their own communication protocol. That got really expensive. It couldn't keep up with the more commercially viable products. And so you now pretty much you see things standardizing on Ethernet and InfiniBand for this kind of field, right? These kind of runs, Ethernet tends to be the thing. And then moving that out of the sensor and into the compute. And every time this stuff moves, every time we have to do compute on it, our ability to take all the data and keep processing it in the stream goes down, right? Every step just adds latency. Every step has a limited capacity in terms of bandwidth. The network maybe has limited bandwidth. And so ultimately, we don't get the maximum value out of our signal all the time. And so part of the drive, right, this data deluge is sort of like, okay, we have to do something, right? So we need to get data off the line as fast as we can and through the computer architecture, right, into the backplane, onto the GPU, where we could do the parallel compute and the math, to do the processing, to run the AI algorithms that turn out to be really good at finding signal hidden deep in really complicated noise, right? This is what detectors like LIGO are using it for. This is what we use it for in radio astronomy and in ultrasound sounds and in CT scans and everything else. And so it turns out these problems at a data science level with radio astronomy data pipelines are kind of similar, a little bit, to the problems we have in medical imaging, which is where our product Holoscan came out of. You just have a bigger parallel data generator, bigger data sets, bigger sensors, higher bandwidth, etc. But conceptually, we want to accelerate that pipeline the same way. And you'll hear lots more about this later. So, but this whole driving deluge of data in terms of instruments, right? That's one huge driver of change. It's one huge driver of demand for compute and data movement. And that kind of takes us to where's the hardware going around AI, right? I want to jump in there just because I want to kind of motivate this that way. So hardware responds to these demands in the environment, right? We have needs. Physicians have needs. Hospitals have needs. Advertisers have needs. And it turns out the needs of advertisers are AI systems to recommend stuff to us very quickly, AI systems to talk to us and engage us more deeply and learn more about us so they can market more stuff to us. But these things are driving a big part of the hardware evolution alongside the sort of advances in science and advances in our desire to do more sensing because we think we can do more with our algorithms and our signal processing. And so today, especially if you're one of these large enterprises, then what you're looking to do is you are looking to build computers not at the computer scale, but at the data center scale, right? We no longer hear big deals being announced in terms of the number of cores or even the number of computers or even the number of racks. Right now in the data center space, in the big OpenAI announcements recently, the unit of scale is the gigawatt of compute, right? So we're moving in this direction where we're building these huge systems. And to build these huge systems, the driver is this massive compute for generative AI, which takes in signals, speech or text, and in this case, a lot of parallel signals, Also multimodal, so starting to pull in images, sound, etc. So the data in is building up. It's still not approaching kind of the scientific levels yet, but it's coming into those kind of ranges. The interesting thing is, as we apply these agentic AIs to these systems, we get input, text, speech, vision, um, and we turn it into tokens. And then we do some processing, and that creates more tokens. And then if we're doing deep research, if we're doing deep thought kind of things, we iterate on those tokens again and again and again until eventually we come to a conclusion. Um, and we may also, as we're going through that, right, the AI may decide, oh, I need to go look something up on the web. And it sends commands off to something else, which goes off, does some things, brings back some results, turns them into tokens, and moves them around. So there's massive amounts of data moving through these data centers. They're somewhat asynchronous. We're looking, again, things are looking for patterns in this sea of data. And so all this hardware is getting faster, latencies are going down, bandwidths are going up, economies of scale are happening, and that's driving the roadmap for uh, both NVIDIA's GPU and CPU compute and other people's. Um, and so what that's really allowing us to do and pushing us to do, frankly, because the algorithms are moving fast, is to release new hardware capabilities on much closer to an annual basis, right? So we have a release and then an upgrade and a kicker and so forth. And so we've talked, our CEO has talked about these products, these names, things that are coming. But it's not just the compute, because as we make the compute bigger, we have to be able to feed it, which means we have to be working just as hard, if not harder, on the communications and the networking. And the demands of these systems are growing faster, right? Moore's law is dead, as they say. We can still, with a process shrink, get more transistors on a die. We can build systems out of chiplets and chip on wafer on substrate kind of things. We can put this stuff together. We can make it bigger. We can put more transistors down, but then we have to feed it. And so we have to spend a lot of effort on the networking. We also need to be thinking about how do we use those transistors as efficiently as possible. And so one of the big things that has come out of the AI revolution, if you will, is a lot of really creative thinking about lower precision data and lower precision processing. And that's a field that, as radio astronomers, you guys have been at the forefront of, hey, my analog to digital conversion doesn't have that many precise bits. I just don't have data that good yet. So being really careful about about your compute and understanding what's significant, what isn't, and where you need to go up to higher precision and where you can stay in a lower precision. And the rest of the world is getting more and more into that boat with you because it's the key to performance. It's the key to getting more than 20, 50% performance improvements. It's the mix of mixed precision, knowing when you need more accuracy, when you need more bits, when you can use less, stringing algorithms together that are careful about that, making sure they only, go back to a lower precision when it's time to do it. But these features are coming fast, right, on an annual basis. And that's, really fast for scientific algorithms to necessarily absorb those changes, for the experiments to happen. But one of the things that, in order to take advantage of all this research that's being done, all this product that's being innovated on, and bring it back into the science to enable more data to be processed, right? To take more of the data off the instruments and do something with it, to look deeper into the signal trying to sort of filter out the noise, trying to dig out more signal, more interesting signal. We need to be looking at these advances that are coming in the hardware, the balance changing in terms of latency and bandwidth in the network as well. Um, we look at CPUs even changing now. And so we're innovating in the CPU space, becoming more memory efficient, especially building higher memory bandwidth, which, as we're trying to stitch together all the baselines and starting to build images, and starting to run image processing, suddenly that memory bandwidth and that memory size that is needed to support the biggest large language models, we can hijack that. We can hijack all of that and we can use it to support our science, especially if we don't have to be living in the double precision world that maybe, uh, you know, traditional scientific computing has always kind of said, oh, we're going to go there. And I think if we can understand where we can take advantage of these new compute paradigms and these massive changes in the ratios of communication and memory bandwidth versus CPU compute and GPU compute, we're going to be in a much better place. So I said I'd try and keep us on track here. So I think I've got 10 minutes left. I think we can make this happen. So AI is driving all this capability, right? It's driving innovation in the hardware. It's driving innovation in the network. It's driving innovation in the software, right? So a big piece that we want to do now is, we're also looking for the AI guys to get more of that capability out closer to the edge, because we can generate more signal, more sensors as cities become smarter, as cars get more sensors on them, as more cars join fleets on the road, as more devices become part of this Internet of Things. There's just too much raw data to move it all to the center. We need to move capability out to the edge. Well, that's exciting as scientists because that means we can put more compute near the sensor, right? It's becoming more energy efficient. It's becoming lower latency. It's accepting higher bandwidths. It can run more complicated algorithms for the same watt and in the same amount of time. And that means we can do more. We can take a little more risk with what we think is interesting to capture and forward on for even further analysis. We can build smarter algorithms at the edge. We can be more adaptive in how we use our sensors and our sensor bandwidth and our data bandwidth back to ultimately back to storage. So, this is not intended to be an NVIDIA sales thing. Really, it's intended to tell you this is the trend, right? We have data center compute, right? Terabits per second, huge amounts of I/O, massive memory bandwidth, big compute, but big energy footprints, requires a lot of cooling. But more and more industrial and embedded applications and even enterprise applications are moving some of that compute out to the edge to take advantage of the ability to step down the data, but get more intelligence closer to the source of the data. And so if we can leverage these technologies in scientific instruments, like they do in the medical community, we can ride that train of annual improvements because they roll down, right? Grace Hopper, the Hopper technology, the Blackwell technology, eventually Rubin and Feynman will roll down into the industrial edge. They won't be as big, they won't take as much power, but they will roll down to the edge. They'll roll down to embedded stuff. It'll be to the point where you can, in a relatively cost-effective way, deploy an awful lot more intelligence, an awful lot closer to whatever antenna or sensor you happen to be interested in. and run more AI out there, not just your regular models, but also more speculative AI models, more, non-linear filtering kind of models. And so we want to ride that wave. We want to catch all that. And that stuff is all trickling down from the data center. So keeping an eye on what the features are that AI is taking advantage of, and what are those headline features that are enabling speed ups, and looking at our algorithms and thinking, hey, how do we apply that? How do we make this real? How do we turn this into a system to detect pulsars? How do we turn it into something to sharpen up our images more, or to do a better job decorrelating the noise, or what have you? Um, and it can pay real benefits, right? This is an example. I think you'll actually have seen or will probably see um, more information from this, but a 4-to-1 reduction in servers, even if the new server takes 50% more power than the old server, if you have a quarter as many of them, you get to go a lot further with your power budget, your cooling budget, your just dollars budget. Um, so these kind of improvements, right? We're not talking 10% improvements generation to generation. We're talking factor improvements if you can use the new capabilities. And that's going to be the key. And that, I think you'll see some other presentations talking about how between the software and the hardware and the increased bandwidth in the network, we can do new things. We can take advantage of these technologies coming from the AI world to do better science and to do more science. And so you may see these slides again. If not, I'm glad that at least you saw them once. The Holoscan SDK is easy to get. It's open source. You can go find it in a bunch of different places. There are also a bunch of reference applications to learn how to use it to get data in and out of the GPU for a bunch of different kinds of sensors and different kinds of use cases to bring that AI um, into the toolkit that you're using um, as you're accepting signal from the universe. So with that, I've hit the end of the slides. I'm 3 minutes or so away from the end of the time. I'd love to take some questions. Otherwise, I'm happy to uh, turn it over to the program organizers again.
Thank you, John. I think I'll just check any questions here for John. There's a question. Jayanta, please.
Yeah, it's a very nice talk, John. I think a lot of information, and I think this is the way radio astronomy should be looking forward. I'm especially kind of amazed to see the NVFP4, which is actually you just mentioned about the black hole architecture. I think that's the next thing which we all should be kind of jumping on it, because radio astronomy don't need precision. You just need a detections, correct? And this is the way to go. I just wanted to ask one thing, like currently you are having, we are kind of experimenting with int8 on TensorRT kind of thing. But when you move to this NVFP4, what kind of speed up we expect for the AI kind of design?
So I will say, like, the FP4, as I understand, it is optimized. Those cores are really optimized for doing sort of AI style matrix and transformer type math. So depending on what you exactly how close to that you can get your problem to look, it might be slower and it might be 20x faster. And it is an annoying fact that we are going to have to adapt our science a little bit to the algorithms that have been optimized, or we don't have to, but we have the opportunity to, right? And so how well can we recast the algorithm in a way that moves it closer to the way the computer wants to do the math, is going to determine how much of that speed up we can gain. But potentially, factor of more than 2, right? You'd expect a factor of 2 just from the bandwidth improvement, but potentially a factor of quite a bit more than that if we can feed the various cores and units the way they need to be fed. And that's always been a challenge in as you're working with interferometry and as the number of baselines grows, right? As the number of signals you want to take in grows, you've always been making trade-offs on the problem size, on the how many of the baselines you actually compute versus how many you could compute, all of this stuff. So we're going to keep making trade-offs.
Yeah. So what I understand, like if you move to a transformer architecture kind of thing, then you said NV4 is already kind of set up for that, correct? And you really get the best out of it.
I mean, it's not just the NV4, right? I mean, the NV4 stuff is set up for, dense matrices and transformers, like all the engines in the GPU. Those are the problems that are generating billions of dollars of revenue. So those are the problems that are getting billions of dollars of research, and those are the functions that are therefore getting maximum acceleration. Other stuff is getting faster too. Like, don't get me wrong, everybody, the rising tide of better bandwidth, better memory management, faster compute, more optimized pipelines, faster networking, everybody wins. But yes, as we get closer to the more your application kind of looks like it's using AI compute building blocks, the more of that acceleration you're going to get to harness. Imagine, sailing with the wind, right? If the closer you can sail to the wind, the faster you can normally go. Obviously, not a great analogy because you can actually do better than that, but you know what I mean.
Yeah, thanks, I think. Yeah.
Thank you. Any other questions for John? Okay, I have one quick question. This is regarding how is the cost, power, and the performance metric go as far as these developments are going?
Well, I think you saw, right, like we talked about I showed a slide with the system, the Coyote system, right? So next gen product for, does the work in one server of 4 servers from before. Depending on where you buy it from, exactly how you configure it, maybe that server is 50 or 80% more than one of the servers you replaced, right? Maybe it's even current market, who knows? Maybe it's 2x. It'll be somewhere between 50% and 2x the price of the old server. But it's doing 4 times the work. So your cost of ownership has gone down considerably. If you look at the big AI systems, the move from Hopper to Blackwell to Rubin, those are getting 100x improvements in TCO. Right? Performance is going up by numbers with zeros at the end of them. And yes, cost is going up by a pretty reasonable factor as well. But when the compute gets so much faster and it uses half the energy per token, right? The tokenomics change. Yeah, it's factors, not percent, better, but the power density goes up, right? The cooling density needs go up. And so that is a factor for some areas and systems, right? We need to think harder about getting the watts out of the box.
Thank you, John. I think there may be other questions. Maybe people would later on get in touch with you. And
Yep, that's great.
thank you for your talk today.
Thank you. Have a great rest of your day.